These are the solutions to activity 3. How many neutrons does a phosphorus 32 atom contain? This is our mass number for the atom, so that would be our number here. The atomic number comes in the periodic table. Phosphorus is element number 15, so we're going to have a sum of the number of protons and the number of neutrons as our mass number of 32. So we subtract the number of protons from 32, we get 17 neutrons for this atom. How many protons and electrons does a sulfide ion contain? Sulfide is specifically S2-. It's the common ion of sulfur. Sulfur is element number 16. Needs to gain 2 electrons to get the nearest noble gas count for that stable count for the sulfide ion of 18 electrons. So S2- has 18 electrons, 16 protons. Silver exists naturally as 2 isotopes, given atomic weights of 106.9051 and 108.9047. What is the abundance of the lighter isotope? Because we have 2 isotopes here, the fraction of the lighter isotope plus the fraction of the heavier isotope has to be equal to 1, meaning if it's, let's say, 75% the lighter, then it would have to be 75% the heavier, or vice versa. So if you know the fraction of 1, you can calculate the fraction of the other, specifically because the element exists only as 2 isotopes. And so then we can write that the average atomic weight for the element of silver would be equal to the fraction of its lighter isotope times the atomic weight of the lighter isotope, and then plus the fraction of the heavier isotope times the atomic weight of the heavier isotope. We have the atomic weight of the lighter isotope, the atomic weight of the heavier isotope given to us in the problem, and then the way we would mathematically solve this problem is to rewrite the fraction of the heavier isotope as 1 minus the fraction of the lighter isotope. Just doing some algebra here, and subbing in for the fraction of the heavier isotope, so we can solve for the fraction of the lighter isotope. Now we have to do a little bit of math. We can be a little bit savvy if we want to, well, maybe these choices won't let us. Sometimes the choices will allow us to maybe determine which of these is right. Let me look at the atomic weight of silver. So we also have to know that we're getting this average atomic weight for the element from the periodic table. So for silver, that's 107.86. 8682. So if we look at this number here, 106.9, 108.9, about 107.9. We're like roughly in between. So this is going to be about 50-50. Now, all of our choices are on 50%, so it doesn't really help us. But if we had a different question where maybe A was 10%, B was 50%, C was 75%, D was, 90%, we would probably be pretty confident in guessing that 50%. So sometimes the choices might be such that we could narrow in pretty easily with just the given information of looking at the average atomic weight, but we just want to set this equal to the fraction of the lighter isotope times 106.9051, and then plus 1 minus the fraction of the lighter isotope times 108.9047. We have to factor this in. We then have to do some rearranging. So let's do the factoring. So we 106.9051 times the fraction of the lighter plus 108.9047, and then minus 108.9047 times the fraction of the lighter. And so if we subtract 108.9047 from both sides, so let's do that math here. So we do 107.8682 minus 108.9047. That's going to equal, let's write this on the right side now, minus 1.0365. That's just this number minus this number, doing some algebra. And then we have to combine our fraction of our lighter isotopes. So I do 106.9051 minus 108.9047. I come up with negative 1.9996 times the fraction of the lighter isotope equals this value here. Everything's in AMU, so the fraction of the lighter, negative 1.0365 divided by 1.9996 negative gives me 51 point, or as a fraction, 0.5184, and so we're going to be 51.8% in that lighter isotope. And the remainder would be the fraction of the heavier isotope, so 48.2% the heavier isotope. Question 4, which is a statement of Dalton's atomic theory. Elements can be converted chemically to each other. This means like we can take carbon in a flask and find some chemical to add to it to convert it to nitrogen. We're not doing that. So we're not able to interconvert elements through simple chemical means. Maybe through some physical processes, elements are interconverting to other elements, maybe through some decay process. Usually we think bigger elements going through these decay cycles, like uranium decaying into some smaller elements. But that's like a physical process. That's not something we can control. That's not something that you're just going to mix up uranium with some stock reagent off the shelf and have that reaction take place. Maybe you can bombard something with neutrons or protons or do some crazy events. We would call those like physical reactions, causing a physical change, but not through simple chemical means. All atoms of a given element are identical. This is a statement of Dalton's atomic theory. It's actually a statement of the theory that isn't entirely true, because we know elements do exist as isotopes, or at least now we know that, but of course that wasn't something that Dalton was aware of or was thinking about at the time in the early 1800s when he was postulating atomic theory. Question 5, what's calcium nitride? Nitride is the simple ion of nitrogen, 3 away from the neon count of electrons. So this atom here has 10 electrons, just like neon. So it has the same configuration of electrons as neon. And then we have calcium with a 2+ charge. That's its ordinary charge. So we end up with this Ca3N2, where we have the combination of the 6+ and the 6-, giving us an overall neutral compound. So it should be Ca3N2. What is the name of BaSO3? So it's barium sulfite. Sulfate is SO4, 2-. Drop this to 3, we change to ite. What is the name of Fe3PO42? Well, let's just back into our charges here. We know phosphate's at 3-. There's 2 of them. We got a 6- from the phosphate, so we have to have a 6+ from the 3 irons. Divide by 3 gives us a 2+ for each of the irons. So this will be iron 2 phosphate. What's the charge and how many oxygen atoms are present in per bromate ion? Well, bromate is BrO3-. It's just like chlorate, ClO3-. Iodine does this too. So we get this systematic behavior for the halogens. So 3, this would be bromate. So if you add an O, go to 4, then that would become per. So per bromate would be 4 oxygens with a -1 charge. So we've got to memorize the charge, memorize what bromate is, understand adding an O goes to per. What is the formula of chromium 6 oxide? Chromium 6 is chromium 6+, oxide is O2-, so it's CrO3. Just remember, the 6 doesn't refer to the number of O's, the number of chromiums. It refers specifically to the charge of chromium. So it's charge expressed as a Roman numeral. Number 10, phosphoric acid. PO4 3- is phosphate. The acid form of 8s goes to ic acid, so we neutralize with H+, add 3 of them to come up with a 3+, 3-. And so this is H3PO4. Now we'll see, this isn't exactly a ionic compound, we're adding H pluses, and they attach to the phosphate ion and make this a molecular compound. Not a big detail, but it'll help us later if we understand that acids are molecular compounds, different from something like K3PO4, which is an ionic compound. A big difference between these designations is ionic compounds tend to have much stronger attraction for the ions in the compound, so really high melting point, compared to molecular compounds, which have usually really low melting points and boiling points, relatively speaking. So just to try to get an understanding of why we might call one molecular and the other ionic. A couple naming, so this would be perchlorate, so this is perchloric acid. Bromic acid would be bromates acid, so HBrO3. And then the name of CBr4, this is a binary molecular compound. Molecular because it contains nonmetal elements. Binary because we have two elements. So this would be carbon for the first element, and then we use tetra to indicate how many bromines we have, so tetrabromide. So this is a different naming system than, say, for K2O, which isn't dipotassium oxide. This is just still potassium oxide. So we got an ionic compound here. We have a molecular compound here, a molecular binary that takes that nomenclature system. 8 carbons saturated with hydrogen. How do we know this is the saturated hydrocarbon? Well, let's count it out. If we want to double check, that's 8. So I get CH3s on the end. The key is just give each carbon 4 bonds. So we got 4 bonds here, that's good. And then let's give this carbon here 4 bonds. That takes 2 hydrogens, and the same for each. So we just go 2 each. And if we notice here, we have a CH3, CH2, 6, CH3. And so that's 6 plus 12 for 18. So this indeed is octane. Propanol, so propane's alcohol, so we would have 3 carbons, and then we're going to replace one of these spots here with the OH group, and the hydrogen atom is in all the other spots. The book discusses 1 versus 2 propanol. Don't worry about the numbering system, just maybe understand that there's 2 spots we could put the hydroxyl group on that, sort of first or second carbon. Those compounds are what we call isomers, but don't worry about naming them in a different fashion. So this would just be propanol. So the formula would be C3H7OH or CH3, CH2, CH2, hydroxyl, etc. Sodium hydrogen phosphate, so Na for sodium, obviously, and then hydrogen phosphate is a hydrogen plus attached to a phosphate 3 minus, kicking this thing down to a 2 minus. So we have an HPO4 2 minus. Sodium, we're going to need 2. So Na, HPO4. I don't need the brackets, so this would just be Na2, HPO4 for sodium, hydrogen phosphate, balancing out the charges. Finally, a couple sig fig questions, or a couple mass questions. This is getting into some chapter 3 topics, a little bit ahead of class for this week, but 1 molecule of CO2, we get the molecular mass. So our mass of 1 molecule, we can just add this up from the periodic table, 12.01 plus 16.00 times 2 for the 2 oxygens. So this is going to be 44.01 AMU. So using the periodic table, we get the mass in the AMU scale. Now, we also could get the molar mass. So this is either AMU, the atomic mass units per atom, or it's grams per mole of each of those elements. So we get 44.01 AMU or 44.01 grams per mole. And so the mass of 1 mole would be 44.01 grams. So notice the same number, very intentional on why this happens. This is because the conversion of AMU to grams is the same conversion factor as the molecule to mole conversion. So one way of thinking of this would be if you say, well, can you show me again, or why is it the number of grams per mole come out to be the same number numerically as the AMU per molecule? Well, it's just how the conversion factors work. We have an Avogadro's number of molecules of CO2 and a mole of CO2. And then we have an Avogadro's number of AMU per 1 gram. It's just a simple conversion factor for gram to AMU. So we're just multiplying and then dividing by Avogadro's number, and hence we get 44.01 grams per mole. And so then what's the mass of 1 molecule of CO2 in grams? Well, let's just do the conversion factor, 6.022. This is rounding it to 4 sig figs, but that's good for most of our problems. If we want to go further, it's just 1,4, so 6.02214 times 10 to the 23 AMU per 1 gram. So the mass of a single molecule of CO2 is going to be really, really small, 44.01 divided by 6.02214 times 10 to the 23, and so that's 7.308 times 10 to the minus 23. Technically, this wanted all of these to just to 3 sig figs. So 44.0, 44.0, 7.31 times 10 to the minus 23 grams. It's a really small mass. And then finally, writing and balancing a combustion reaction of a hydrocarbon. So hydrocarbons combust to form CO2 and water. So C4H10 reacts with oxygen gas from air while it burns to produce CO2 and water. So I'm going to get 5 waters. That's going to end up giving me a fraction for oxygen. So I'm going to go ahead and double that to 10, double this to 2. And then that's going to give me 8 CO2s. And then I'm going to have 5 oxygens plus 8, so 13 O2s. And so that's 26 O's on both sides. 26 O's on both sides, and 16 plus 10, 26 O's. So just making sure I have the oxygens in balance on both sides, 8 carbons on both, 20 hydrogens on both. So that's our balanced combustion reaction for that reaction of butane. And then write and balance the reaction for the formation of aluminum oxide from the elements aluminum and oxygen. We had written this, I think, all the way back on day 1, but here we can actually understand that our elements are going to react to form a compound that forms the stable ions of each, so Al3 plus, O2 minus, so Al2O3. And so then the way the balancing can work here, odd number, even number, so let's do 3 and 2. Gives me 6 O's on both sides, and let's put 4 aluminums on the reactant side. So problems next week, we'll start to get into how many grams of product can you make, how much of one reactant reacts with another reactant, what's a limiting versus excess reactant problem, and how would we work that out. So that's it for this video. Thank you for your attention.